Hello everybody, in this video we're going to be discussing trigonometric parametric equations, which sounds actually, of course, really worrisome. But you know what, don't worry about it. As a matter of fact, what we're going to be doing much of the time with trigonometric parametric equations, we can convert them into just respect to x and y, which would be a lot easier to graph. But the fact of the matter is this. With trigonometric parametric equations, what we're doing is, instead of using the parameter of t, which of course, as you recall, t was used most of the time to represent time, as you know, x and y as being functions of time. That way we could identify times for positions. But sometimes we want to let the parameter be theta, and of course, recall that theta would represent an angle. So we say whatever x and y are, or x and y values, they would necessarily be defined with respect to an angle theta as opposed to with respect to a time t. So here's the thing about it. Let's say we necessarily wanted to sketch the curve of x equals 3 cosine theta. Let's go with the sign here. Y is equal to 4 sine theta. Okay, anyways, let's go ahead and let these be our parametric equation components here. But we say x and y are defined as these. Fact of the matter is, though, we could do this. But again, you know, making a table is kind of tedious and boring, and really, who wants to do that? So here's what we're going to do. We're going to go ahead and express this in terms of just x and just y. And in order to do so, we're going to go ahead and eliminate the parameter here, which in this case, the parameter is theta. So here's what we're going to do, actually. There's a convenient method, or a little bit of sleight of hand we're going to use here. But what we're going to do is we're going to solve for cosine of theta and sine of theta in both equations, okay? So in this first case, we had x was equal to 3 cosine theta, and we want to solve for just cosine theta. So what we'll end up doing here is we'll just extend our vinculum there and divide by 3. But here's what we've got. We say, okay, so cosine of theta is equal to x over 3, a very, very splendid trig ratio there. And we say, okay, so now y being, you know, 4 sine theta, we could divide both of these by 4, but again, the reason why we're doing this is necessarily to, you know, isolate sine and cosine for our nifty trick that we're going to be using here. But the nifty trick actually borrows upon this identity that we use in trigonometry, the Pythagorean identity. And you know, pardon everybody out, you know, me, for maybe making some people mad there. I put sine first, and kind of a bad habit. But we say sine squared plus cosine squared is 1, or cosine squared plus sine squared is 1. But the fact of the matter is, we have solved for cosine and sine of theta, which was our parameter here, with respect to x and y. So here's what we're going to end up doing. We say, okay, so if sine squared theta is plus cosine squared theta is 1, we say, and sine squared theta is y over 4. We say, okay, so y over 4 necessarily squared, plus, now in this case, cosine squared theta, which was, cosine theta was x over 3, so cosine squared theta is x over 3 squared, and this is equal to 1. We're going to go ahead and do a little magic here. We say, okay, so y squared over 16, and this is plus x squared over 9, and this is equal to 1. I know what you're thinking to yourself, or maybe not, because you're not a dork like me, but hey, oh my goodness, this is almost the equation of a circle. And I'm going to go ahead and do a little rearranging here. We say, so x squared over 9 plus y squared over 16. And this is so totally 1. But the fact of the matter is this. If this were a circle, of course, we'd have a common radius. And both of these numbers down here would be the same. But, alas, they are not. So here's what we're going to end up doing instead is we're going to treat this as an ellipse. And here's what I want to do. Just go ahead and identify a few things. Now, 16 having a larger magnitude, we're going to say that's a squared. And so if a squared is equal to 16, then we know a is equal to 4. And so that distance right there is merely the distance from the center of the ellipse out to the vertices on with respect to the major axis here. And we say, okay, so if this is b squared here, and b squared is 9, we say then b must be 3. And that's no more than our minor axis distance, okay? And then we'll have to solve for c here, it being an ellipse. But the fact of the matter is this. We can go ahead and take a look at this with respect to it being in standard form. And keep in mind, I'm going to go ahead and rewrite this one more time down here. This is really x minus 0 squared over 9 plus, now y minus nothing squared over 16, and this is 1. So the fact of the matter is the center here is at 0, 0. So it's centered at the origin. We say, okay, so 0, 0. We say, okay, so on its major axis, which in this case, since the bigger number here was underneath y, its major axis is vertical. We say we'll go up 4, 1, 2, 3, 4, and here's one vertex, and we say down 4, 1, 2, 3, 4. That was kind of a bad line. And then on its minor axis, since the minor axis is it's the smaller number, but it's horizontal in this case, we'll go 3 out in each direction here. 1, 2, 3, 1, 2, 3. And of course, the last thing we could do necessarily is find the two foci of this. But hey, who said we had to in this one? Unless I asked for it. I mean, we could do it then. So we say, here's our ellipse, right? Yeah. And of course, again, we could totally do this with our parametric equations. They do the same thing. But the fact of the matter is, it's a lot easier to do it when you've got it as the equation of an ellipse in standard form. So enjoy.